Tonight, we stand at the ultimate frontier, where existence itself may end and the unknown begins. We are cosmic explorers, preparing to ask the most profound boundary question ever contemplated by human consciousness. What lies beyond the edge of the universe? It's a question that has haunted philosophers and physicists, mystics and mathematicians, anyone who has ever looked up at the night sky and wondered where it all ends. Imagine standing at the shore of a vast cosmic ocean, with waves of starlight lapping at the boundaries of everything we can see or know. Behind you stretches the familiar territory of galaxies and nebulae, the comfortable archipelago of known space where planets orbit, stars and matter behaves according to the laws we understand. But ahead, beyond the cosmic horizon, lies something that challenges the very concept of existence itself. The edge we seek isn't like the edge of a table or the shore of a lake. It's not a wall where the universe stops and something else begins. It's far stranger and more subtle, a boundary created by the fundamental nature of space, time, and information itself. It's an edge that may not exist as a physical barrier, yet defines everything we know and can ever know about reality. This boundary has multiple faces, each revealing different aspects of the ultimate mystery. There's the edge of what we can see, the cosmic horizon beyond which light hasn't had time to reach us since the universe began. There's the edge of what we can ever see, the retreat boundary, created by the accelerating expansion of space itself. And there might be edges we haven't yet imagined, boundaries imposed by the fundamental nature of reality at its deepest levels. The very question reveals the remarkable nature of human consciousness. We are patterns of matter and energy that have become complex enough to contemplate their own cosmic context, to wonder about boundaries that exist billions of light years away and perhaps infinitely far beyond. In asking what lies beyond the edge, we're really asking what it means to exist within limits, what it means to be finite beings, contemplating infinite possibilities. The answers we'll explore tonight range from the comfortingly familiar to the mind-bendingly strange. Perhaps beyond our cosmic horizon lies simply more of the same endless galaxies, stars, and planets extending forever in all directions. Perhaps we live in one bubble universe among countless others, each with its own laws of physics and its own edge to contemplate. Perhaps the universe curves back on itself like the surface of a sphere, making the very concept of an edge meaningless. Or perhaps the answer is far stranger still. Perhaps we live in a cosmic simulation with computational boundaries that create natural edges to existence. Perhaps space itself becomes granular and pixelated at ultimate scales, breaking down into quantum foam where the very concepts of beyond and edge lose their meaning. The journey we're about to take will stretch your imagination to its limits and perhaps beyond. We'll explore the observed boundaries of the cosmos, where the most powerful telescopes reveal the furthest galaxies as they existed billions of years ago. We'll venture into theoretical realms where mathematics suggests possibilities that challenge every assumption about the nature of existence. We'll discover that the edge of the universe is not just a cosmological concept, but a mirror reflecting the boundaries of human consciousness itself. In contemplating cosmic edges, we confront our own limitations, our own mortality, our own place in the vast tapestry of existence. The beauty of this exploration lies not just in the potential answers, but in the questions themselves. Some mysteries are so profound that simply asking them transforms our understanding, even if definitive answers remain beyond our reach. The edge of the universe is such a mystery, a koan written in the language of cosmology, inviting us to expand our consciousness to encompass the inconceivable. As we begin this journey tonight, let your mind become as vast and open as the cosmos itself. Release the comfortable assumptions about beginnings and endings, about inside and outside, about here and there. We're about to explore territories where such concepts might lose their meaning entirely, where the familiar landmarks of human experience fade into the profound unknown. Tonight, we discover that the edge of the universe is not just a destination, it's a transformation of perspective, an invitation to see existence itself with new eyes. We learn that consciousness and cosmos are more intimately connected than we ever imagined, and that the boundaries we seek might be reflections of the very awareness that seeks them. Let the ultimate frontier beckon, and prepare to journey beyond the edge of everything. The observable universe presents us with one of the most beautiful paradoxes in all of cosmology. As you contemplate the night sky from your quiet vantage point on Earth, You're looking at a sphere of space roughly 93 billion light-years in diameter, yet the universe is only 13.8 billion years old. How can we see farther than light has had time to travel? The answer reveals the dynamic, breathing nature of space itself. When we peer deep into space with our most powerful telescopes, we're also looking backward in time. The light from distant galaxies left them billions of years ago, carrying images of cosmic youth across the expanding vastness to reach our eyes today. But here's where the story becomes wonderfully complex. During the billions of years that light was traveling toward us, space itself was expanding, carrying those distant galaxies even farther away. Imagine a cosmic conveyor belt running backward beneath a marathon runner. The runner moves forward at a steady pace, but the belt carries her starting point ever further behind her. Similarly, light from distant galaxies travels toward us at the constant speed of light, but the expansion of space carries the source galaxies ever further away during the light's journey. This expansion means that a galaxy whose light took 10 billion years to reach us is not 10 billion light-years away today. It's much farther. The space between us and that galaxy has been stretching throughout the light's journey, so the galaxy that appeared 10 billion light-years away when its light began, the journey might be 25 billion light-years away by the time we receive that ancient light. The cosmic microwave background radiation represents the ultimate horizon of our visual exploration. This faint glow, discovered accidentally in the 1960s by Arno Penzias and Robert Wilson, is the afterglow of the Big Bang itself, the moment when the universe first became transparent to light. Before this epoch, roughly 380,000 years after the Big Bang, the universe was opaque, filled with hot plasma that scattered photons in all directions. This surface of last scattering creates a natural boundary to optical observation. No telescope, no matter how powerful, can see beyond this cosmic dawn. It's like trying to see beyond the surface of the sun. The light comes from an opaque layer that blocks our view of whatever lies deeper. The cosmic microwave background forms a spherical shell around us, the most distant thing we can ever see with light-based observations. The patterns in this ancient light tell the story of the universe's youth, tiny temperature fluctuations that would eventually grow into the cosmic web of galaxies and galaxy clusters we see today. These fluctuations, mapped with exquisite precision by satellites like COBE, WMAP, and Planck, represent quantum fluctuations from the universe's inflationary epoch, stretched to cosmic scales by the rapid expansion of space. But even this ultimate visual horizon doesn't represent the edge of the universe, only the edge of what we can see. The cosmic microwave background is like the wall of a vast room illuminated by a single candle. We can see the wall clearly, but we cannot see what lies beyond it in the darkness. There might be infinite space extending beyond our observable horizon, filled with galaxies and structures we can never detect. The geometry of our observable universe is remarkably close to flat, according to precision measurements of the cosmic microwave background. This flatness has profound implications for what lies beyond our horizon. In a flat universe, the simplest assumption is that space extends infinitely in all directions, with more galaxies, more stars, more planets continuing forever beyond our ability to observe them. The statistical properties of the observable universe suggest remarkable uniformity on the largest scales. Galaxy clusters are distributed roughly evenly, the cosmic microwave background shows only tiny fluctuations, and the large-scale structure appears to follow the same patterns in every direction we look. This cosmic democracy suggests that the regions beyond our horizon are probably similar to what we can observe. Recent observations have pushed our vision to unprecedented depths. The Hubble Space Telescope's deep-field observations revealed galaxies existing when the universe was less than 1 billion years old. The James Webb Space Telescope is now detecting galaxies from even earlier epochs, showing us the universe when it was only a few 100 million years old, nearly at the limit of when the first stars could have formed. These observations reveal that the universe was already rich with structure at remarkably early times. Massive galaxies existed when the universe was young, suggesting that the process of cosmic evolution began almost immediately after the cosmic dark ages ended. The continuity of this structure right to the edge of the observable universe hints that similar processes continue beyond our horizon. The particle horizon, the boundary of what we can theoretically observe, continues to grow as the universe ages. Every year, light from slightly more distant regions reaches us for the first time, expanding our observable universe by 1 light-year in radius. However, this growth is now being overtaken by the acceleration of cosmic expansion, which is beginning to shrink our future light cone. The edge of the observable universe is not a static boundary, but a dynamic frontier, constantly changing as space expands and light continues its journey across the cosmos. Standing at this frontier, we realize that we are cosmic archaeologists, using ancient light to reconstruct the history of everything we can see, while the regions beyond remain tantalizingly hidden in the darkness beyond observation. As you contemplate this vast sphere of observable space surrounding Earth like a cosmic bubble, consider that you are situated at the exact center of your own observable universe, not because Earth is special, but because the observable universe is defined by what can be seen from your particular location in space and time. In the 1920s, a quiet astronomer named Edwin Hubble made observations at Mount Wilson Observatory that would forever change humanity's understanding of the cosmos. Studying the light from distant galaxies, Hubble discovered something that contradicted every assumption about the universe. The galaxies were all moving away from us, and the farther away they were, the faster they were receding. This discovery revealed the universe to be not a static, eternal structure, but a dynamic, expanding entity where space itself is stretching. The implications were staggering. If galaxies are moving apart today, they must have been closer together in the past. Extrapolated backward, this led to the revolutionary concept of the Big Bang, a moment when all of space and matter emerged from an infinitely dense point. But Hubble's discovery revealed something even stranger about the cosmic edge. The expansion of space means that the most distant galaxies are receding from us faster than the speed of light. This doesn't violate Einstein's special relativity, which prohibits matter from moving through space faster than light. Instead, it's space itself that's expanding, carrying distant galaxies away from us at superluminal speeds. Imagine dots painted on the surface of a balloon. As you inflate the balloon, the dots move apart from each other, but they're not moving through the rubber surface. The surface itself is expanding, carrying the dots along with it. Similarly, galaxies don't move through space at these tremendous speeds. Space itself expands, carrying galaxies along like leaves on a flowing river. This expansion creates a peculiar boundary called the Hubble horizon. At a distance of roughly 14 billion light-years from Earth, the recession velocity of space equals the speed of light. Galaxies beyond this distance are receding faster than light can travel toward us, creating a natural barrier to observation and communication. Light from these super-distant galaxies can never reach us, no matter how long we wait. But the story becomes even more mysterious when we consider dark energy, the unknown force discovered in the 1990s that's causing cosmic expansion to accelerate. Until the late 1990s, astronomers assumed that gravity would gradually slow the expansion of the universe, perhaps even reversing it into a big crunch. Instead, observations of distant supernovae revealed that the expansion is speeding up. Dark energy, comprising roughly 68% of the universe, is stretching space at an ever-increasing rate. This acceleration has profound implications for the cosmic edge. Galaxies that we can see today will eventually disappear beyond our horizon as their recession velocities exceed the speed of light. The observable universe is actually shrinking in terms of what we will be able to see in the far future. This creates what cosmologists call the event horizon, the boundary separating regions of space that we can potentially observe from regions we can never observe, no matter how long we wait. As dark energy continues to accelerate expansion, this event horizon is moving inward, eventually encompassing only our local group of galaxies. The mathematics describing this expansion are elegantly simple, yet profoundly mysterious. The Hubble constant, measured to be approximately 70 kilometers per second per megaparsec, describes how fast space expands at different scales. For every million parsecs, roughly 3.26 million light-years of distance, space expands by 70 kilometers per second. This means that truly distant galaxies are receding at significant fractions of the speed of light. The acceleration of expansion is described by an equation of state parameter that remains one of the deepest mysteries in physics. Dark energy behaves like a fluid with negative pressure. It pushes space apart rather than pulling it together. This anti-gravitational effect dominates the large-scale behavior of the universe, overwhelming the attractive influence of matter and dark matter. Recent observations have revealed the detailed history of cosmic expansion. The universe actually experienced multiple epochs. An initial period of extremely rapid expansion called cosmic inflation, a long period of decelerating expansion dominated by matter, and the current epoch of accelerating expansion driven by dark energy. Each epoch created different boundaries and horizons in the cosmic landscape. The cosmic expansion also affects the nature of light itself as it travels across these vast distances. Photons get stretched along with space, shifting their wavelengths toward the red end of the spectrum in a process called cosmological redshift. The most distant galaxies we observe are redshifted so dramatically that their ultraviolet light appears as infrared radiation by the time it reaches us. This stretching of light creates a natural limit to observation. As galaxies recede to greater and greater distances, their light becomes increasingly redshifted and dimmed. Eventually, the light becomes so faint and so redshifted that it falls below the detection threshold of any conceivable telescope. The universe effectively fades to black beyond a certain distance. The expansion of space also affects the flow of time itself, through the intricate relationships described by general relativity. Observers in different cosmological epochs would experience time differently, and the very definition of simultaneity becomes complex across cosmic distances. When we observe distant galaxies, we're not just seeing them at different locations, but at different stages of cosmic history. Future observations will continue to probe the nature of cosmic expansion and its implications for cosmic boundaries. Next-generation telescopes and gravitational wave detectors may reveal new aspects of how space expands and what drives the mysterious dark energy. These discoveries could fundamentally change our understanding of where the universe is heading and what kinds of edges or boundaries might exist in our cosmic future. As you consider the expanding space around you, realize that every breath you take occurs in a universe slightly larger than it was a moment before. The cosmic expansion that carries distant galaxies beyond our reach is the same process that stretches through every region of space, including the air in your lungs and the atoms in your body. Though gravitational and electromagnetic forces easily overcome expansion's effects on these smaller scales, the runaway expansion of space creates the ultimate horizon, a boundary defined not by what exists, but by what can possibly be reached or observed from our cosmic address in an accelerating universe. The edge of the universe is not a single, simple boundary, but a complex family of horizons, each defining different aspects of cosmic limits and revealing different truths about the nature of existence itself. Understanding these various edges requires us to think carefully about what we mean by seeing, reaching, and existing on cosmic scales. The particle horizon represents the boundary of everything we have ever been able to observe since the Big Bang. Light from objects at this distance has been traveling toward us for the entire 13.8 billion year history of the universe. This creates a sphere around us with a radius of about 46.5 billion light-years, larger than 13.8 billion light-years, because space has been expanding during the light's journey. But the particle horizon is constantly growing. Each moment, light from slightly more distant regions reaches us for the first time, expanding our observable universe. If we could wait forever, and if cosmic expansion weren't accelerating, this horizon would eventually encompass arbitrarily distant regions of space. Every point in an infinite universe would eventually become observable, given enough time. The event horizon tells a different story entirely. This boundary separates the regions of space that we can theoretically reach or communicate with from those that remain forever beyond our causal influence. In an accelerating universe driven by dark energy, this event horizon is actually shrinking. Galaxies that we can see today are being carried beyond this boundary, disappearing forever from our potential reach. The Hubble horizon, roughly 14 billion light-years away, marks the distance where the recession velocity of space equals the speed of light. This boundary has a peculiar property. Light emitted by galaxies exactly at the Hubble distance will hover at a constant distance from us, neither approaching nor receding. Light from galaxies beyond the Hubble horizon is actually carried away from us by expanding space, even as it travels toward us at the speed of light. Each of these horizons creates different philosophical implications for the nature of existence and reality. The particle horizon suggests that the universe contains regions that exist, but remain fundamentally unobservable to us. The event horizon implies that there are parts of the universe with which we can never interact, no matter how advanced our technology becomes. The Hubble horizon reveals the strange relativity of motion in an expanding universe. Cosmological horizons also exist in different theoretical models of the universe. In a closed universe with positive curvature, space curves back on itself like the surface of a sphere. In such a universe, there might be no edge at all. You could travel in any direction and eventually return to your starting point, just as you can circumnavigate Earth without ever reaching an edge. In a flat or open universe, space extends infinitely in all directions, making the concept of a cosmic edge more subtle. The boundaries become observational and causal rather than physical. There's always more space beyond any point you could reach, but practical limitations of light speed and cosmic expansion create natural boundaries to observation and interaction. The cosmic event horizon has properties remarkably similar to the event horizon of a black hole. Just as information from matter falling into a black hole becomes increasingly redshifted and time-dilated as it approaches the event horizon, information from galaxies approaching our cosmic event horizon becomes increasingly difficult to detect. The parallels suggest deep connections between black hole physics and cosmology. Causal boundaries represent perhaps the most fundamental type of cosmic edge. These boundaries separate regions of spacetime that can potentially influence each other from those that remain forever causally disconnected. In general relativity, no influence can propagate faster than light, so cosmic expansion creates causal boundaries that limit which regions of the universe can affect each other. The distinction between coordinate boundaries and physical boundaries becomes crucial when discussing cosmic edges. Coordinate boundaries arise from the mathematical systems we use to describe spacetime, like the coordinate singularity at the north pole of Earth that exists in our mapping system but doesn't correspond to any physical boundary on the USIC's planet's surface. Physical boundaries, if they exist, would represent genuine edges to space, time, or matter. But general relativity and quantum mechanics suggest that such hard boundaries are probably impossible. Space and time appear to be infinitely divisible, and quantum mechanics prohibits sharp boundaries in the properties of matter and energy. Information theoretic boundaries provide another perspective on cosmic edges. If the universe is fundamentally computational, as some theories suggest, then there might be natural limits to how much information can be processed or stored in any finite region of space. These information boundaries could create effective edges to complexity and computation, even in an infinite universe. The holographic principle suggests that all the information in any volume of space can be encoded on its boundary surface. This creates a hierarchy of boundaries. Each region has an information boundary that contains complete information about everything inside it. The ultimate boundary would be the surface containing information about the entire universe, if such a surface exists. Quantum mechanical boundaries emerge from the fundamental uncertainty principles governing matter and energy. At the Planck scale, roughly 10 (-35 meters) and 10 (-43 seconds), quantum fluctuations become so violent that the classical concepts of space and time break down. This might represent the ultimate boundary of physical description, beyond which our current physics cannot meaningfully be extended. Topological boundaries describe the overall shape and connectivity of the universe. Even an infinite universe could have interesting topological properties. It might be infinite in extent but finite in volume, like a three-dimensional analog of the surface of a torus. Such topological boundaries would create strange connection patterns, where distant regions of space are actually connected through hidden geometric relationships. As you contemplate these multiple meanings of cosmic boundaries, realize that each type of edge reveals different aspects of the relationship between consciousness and cosmos. The boundaries we discover depend on the questions we ask and the methods we use to explore them. The edge of the universe becomes a mirror reflecting our own conceptual limitations and possibilities. When astronomers point their telescopes toward the deepest reaches of space, they become cosmic cartographers, attempting to map territories that challenge the very concept of boundaries. The most distant galaxies appear as they existed when the universe was young, their ancient light carrying information across billions of years to reach our instruments today. The Hubble Space Telescope's deep-field observations revolutionized our understanding of the cosmic edge by revealing that even the apparently empty regions of space teem with distant galaxies. By pointing the telescope at tiny patches of seemingly dark sky and exposing them for hundreds of hours, astronomers discovered thousands of galaxies in regions no larger than a grain of sand held at arm's length. These deep-field images show galaxies existing when the universe was less than 1 billion years old, providing glimpses of cosmic youth that help us understand what might exist beyond our observational reach. The galaxies appear remarkably mature for their young age, with complex structures and active star formation already well underway. This suggests that galaxy formation began almost immediately after the cosmic dark ages ended. The James Webb Space Telescope, with its unprecedented infrared capabilities, is now pushing even deeper into cosmic history. Its observations reveal galaxies that existed when the universe was only 300 to 400 million years old, nearly at the theoretical limit of when the first stars could have ignited. These ancient galaxies appear surprisingly massive and structured, challenging our understanding of early cosmic evolution. Statistical analysis of galaxy distributions provides powerful tools for extrapolating beyond observational limits. By measuring how galaxies cluster together on different scales, astronomers can predict the statistical properties of regions beyond our horizon. The cosmic web of galaxy filaments and voids appears to continue with similar patterns to the edge of the observable universe, suggesting that these structures extend indefinitely beyond our sight. Large-scale structure surveys like the Sloan Digital Sky Survey have mapped millions of galaxies, revealing the cosmic web in unprecedented detail. These surveys show that matter organizes itself into a foam-like pattern of filaments and voids that remains remarkably consistent across all observable scales. The largest structures we observe, galaxy superclusters spanning hundreds of millions of light-years, appear to be embedded in even larger patterns that extend to our observational limits. The cosmic microwave background provides our most detailed map of the universe's edge conditions. The tiny temperature fluctuations in this ancient radiation, mapped with extraordinary precision by the Planck satellite, show the quantum fluctuations that seeded all subsequent structure formation. These fluctuations follow statistical patterns that suggest they continue beyond our horizon with similar properties. Gravitational lensing offers another window into the cosmic edge. When the gravity of massive galaxy clusters bends and magnifies light from more distant objects, it creates natural telescopes that allow us to observe galaxies that would otherwise be too faint to detect. These gravitational lenses reveal that galaxy formation was already active at the earliest epochs we can observe. The most distant individual objects we can detect, quasars powered by supermassive black holes, provide crucial information about conditions near the edge of the observable universe. These brilliant beacons existed when the universe was less than 1 billion years old, yet they're powered by black holes containing millions or billions of solar masses. Their existence implies rapid early formation of massive structures throughout the universe. Type Ia supernovae serve as standard candles for measuring cosmic distances and mapping the expansion history of the universe. Observations of these stellar explosions at various distances revealed the accelerating expansion driven by dark energy. They also provide information about the chemical composition and stellar populations of galaxies near the edge of the observable universe. Gamma-ray bursts, the most energetic explosions in the universe, can be detected across vast cosmic distances due to their extreme brightness. These catastrophic events, probably involving the collapse of massive stars or the merger of neutron stars, provide snapshots of star formation and stellar death in the earliest epochs of cosmic history. The homogeneity and isotropy observed in deep surveys support the cosmological principle, the assumption that the universe looks roughly the same in all directions and at all scales when viewed from any typical location. This principle suggests that regions beyond our horizon probably contain similar densities of galaxies, stars, and planets arranged in similar large-scale patterns. However, some observations hint at possible violations of perfect homogeneity on the largest scales. The axis of evil in the cosmic microwave background and potential correlations in distant quasar orientations suggest that the universe might have subtle preferred directions or asymmetries. If confirmed, These would imply that regions beyond our horizon might differ systematically from what we observe. Future observational capabilities will continue pushing the boundaries of cosmic cartography. The upcoming extremely large telescopes will resolve individual stars in distant galaxies, providing detailed information about stellar populations and formation histories near the edge of the observable universe. Space-based gravitational wave detectors might detect the coalescence of the first black holes formed in the universe. The theoretical limits to observation are set by fundamental physics rather than instrumental capabilities. The cosmic microwave background represents an ultimate horizon for electromagnetic observations. No optical or radio telescope, regardless of size or sensitivity, can see beyond the surface of last scattering. However, other forms of radiation might penetrate deeper into cosmic history. Cosmic neutrinos, produced in the first few seconds after the Big Bang, could theoretically provide information about even earlier epochs. The cosmic gravitational wave background, produced during inflation itself, might carry information about the universe's birth that electromagnetic radiation cannot access. These exotic forms of observation could extend our cosmic maps beyond current limits. As you contemplate the vast cosmic surveys that map billions of galaxies across billions of years of cosmic history, realize that each point of light represents an entire cosmos of stars, planets, and possibly civilizations. The maps we create reveal not just the distribution of matter in space, but the distribution of possibilities for complexity, consciousness, and meaning throughout the universe. Perhaps the most profound answer to what lies beyond the edge of the universe is also the simplest: more of the same, extending infinitely in all directions. This possibility, an infinite universe filled with endless variations of galaxies, stars, planets, and perhaps life itself, carries implications so vast that the human mind struggles to comprehend their full meaning. The cosmological principle, one of the fundamental assumptions of modern cosmology, suggests that the universe appears roughly the same from any typical vantage point. If you could travel to any galaxy in the observable universe and look around, you would see a similar density of matter, a similar cosmic web of structure, and similar physical laws governing the behavior of matter and energy. If this principle extends beyond our observational horizon, then the regions we cannot see probably contain more galaxies arranged in similar patterns, governed by the same physical laws, following the same evolutionary processes that have shaped the cosmos we observe. The cosmic web of filaments and voids would continue indefinitely, with galaxy clusters forming and evolving according to the same gravitational dynamics that operate in our cosmic neighborhood. In an infinite universe filled with matter, every possible arrangement of atoms would occur somewhere, simply by virtue of infinite space, providing infinite opportunities for different combinations. This leads to one of the most mind-bending implications of cosmic infinity. If matter is distributed, even roughly uniformly, throughout infinite space, then there must be exact duplicates of everything, including you. The mathematics of infinity, combined with finite particle arrangements, creates this startling conclusion. There are only so many ways that atoms can be arranged within any finite volume of space, a large number, but still finite. In infinite space, every possible arrangement must occur not just once, but infinitely many times. Somewhere in the vast reaches beyond our horizon, there would be exact copies of Earth, exact copies of every person who has ever lived, exact copies of every moment that has ever occurred. These cosmic doppelgangers wouldn't be in some parallel dimension or alternate timeline. They would exist in the same physical universe as us, just unimaginably far away. The distance to the nearest exact copy of yourself has been calculated to be roughly 29 meters away, a number so large that writing it out would require more digits than there are atoms in the observable universe. But infinity doesn't stop with mere exact copies. It demands infinite variations on every theme. There would be versions of Earth where the continents are slightly different, where history unfolded differently, where you made different choices at crucial moments. There would be versions where humanity developed differently, where different species became dominant, where the laws of physics operate in the same way, but initial conditions created different evolutionary paths. The implications extend to every scale of cosmic structure. Somewhere in infinite space, there would be galaxy clusters identical to our local group, but with small variations. Perhaps the Andromeda Galaxy approached the Milky Way from a different angle, Or perhaps additional galaxies joined the gravitational dance. Every possible variation of cosmic structure would exist somewhere in the infinite expanse. This infinite diversity within infinite repetition creates what cosmologists call the infinite monkey theorem, applied to cosmic scales. Just as infinite monkeys typing randomly would eventually produce the complete works of Shakespeare, infinite cosmic evolution would eventually produce every possible form of complexity, intelligence, and consciousness. The statistical predictions of infinite space have been worked out in remarkable detail by theoretical physicists. In a universe with roughly uniform matter density extending infinitely, the nearest solar system similar to ours would be expected at a distance of about 10-24 light-years. The nearest exact duplicate of our solar system would be much farther, perhaps 10-100 light-years away. These distances are so vast that they make the observable universe seem tiny by comparison. Light from these cosmic duplicates could never reach us, and we could never reach them, no matter how advanced our technology becomes. They exist in permanent causal isolation, playing out stories identical to ours or variations on cosmic themes we've never imagined. The philosophical implications of infinite cosmic repetition challenge our understanding of uniqueness, significance, and meaning. If everything that can happen does happen infinitely many times throughout infinite space, what makes any particular occurrence special or meaningful? How do we understand individual identity and significance in a cosmos where every possible version of ourselves exists? Yet rather than diminishing meaning, cosmic infinity might actually enhance it. Every moment of consciousness, every experience of beauty, every act of love and creativity occurs not just once, but infinitely many times throughout the cosmos. The patterns of meaning that emerge from consciousness and complexity are not rare accidents, but fundamental features of infinite cosmic evolution. The observational evidence for infinite space remains indirect but compelling. Precision measurements of the cosmic microwave background suggest that the universe is geometrically flat to within observational error. In general relativity, a perfectly flat universe extends infinitely in all directions, while any deviation from flatness would curve space into a finite but boundaryless structure. Recent observations from the Planck satellite have constrained the geometry of space to be flat within a margin of error of less than 1%. This suggests that the universe is either exactly flat and therefore infinite, or so close to flat that it would be vastly larger than the observable universe, even if technically finite. The uniformity observed in the cosmic microwave background supports the idea that similar conditions extend far beyond our horizon. The temperature variations are remarkably small and follow statistical patterns that suggest they continue with similar properties throughout space. This cosmic democracy argues for similar physical processes operating throughout an extended or infinite universe. As you contemplate the possibility of infinite space filled with endless variations on cosmic themes, consider that your consciousness is experiencing one particular realization of infinite possibilities. The thoughts forming in your mind, as you read these words, are part of the universe, exploring its own infinite creative potential, understanding itself through countless perspectives scattered throughout endless space. In infinite space, the journey beyond the edge becomes not a destination but a recognition, the realization that there is no edge, only endless continuation of the cosmic story in infinite variations, each as real and meaningful as the one you're experiencing right now. Beyond the edge of our observable universe might lie not just more space, but entirely different universes, bubble cosmos, with their own laws of physics, their own fundamental constants, their own unique ways of organizing matter and energy into complex structures. This is the breathtaking possibility suggested by eternal inflation theory, one of the most ambitious ideas in modern cosmology. The theory of cosmic inflation, developed in the 1980s by Alan Guth and others, proposes that the universe underwent a period of exponential expansion during its first fraction of a second. This rapid stretching of space would explain many puzzling features of the cosmos, including its remarkable flatness and the uniformity of the cosmic microwave background across vast distances. But inflation theory carries a startling implication. If inflation happened once, it probably happens everywhere and eternally. The quantum fields that drive inflation behave probabilistically, starting and stopping inflation in different regions of space at different times. While inflation ended in our region about 13.8 billion years ago, allowing matter and radiation to form the hot Big Bang cosmos we inhabit, it might continue forever in other regions. This creates a cosmic landscape of bubble universes nucleating within an eternally inflating background spacetime. Each bubble represents a region where inflation ended and normal physical processes began, creating what we would recognize as a universe filled with matter, radiation, and the potential for complex structure formation. Our observable universe would be just a tiny portion of one such bubble. The mathematics of eternal inflation suggest that these bubble universes form continuously throughout endless time and space. The inflating background space expands faster than individual bubbles can grow, ensuring that there's always room for new universes to nucleate. The result is an infinite fractal structure of bubble universes embedded in eternally expanding space. Each bubble universe could have different physical properties determined by how the inflation field decays when that bubble forms. The fundamental constants of physics, the strength of gravity, the mass of the electron, the speed of light, might vary from bubble to bubble. The number of spatial dimensions could differ, the forces of nature might be unified in different ways, and the very concepts of space and time might operate according to different principles. String theory provides a framework for understanding this diversity of physical laws. The theory suggests that the fundamental constants of physics are determined by how extra spatial dimensions are curled up at microscopic scales. Different ways of compactifying these extra dimensions lead to different low-energy physics, creating what theorists call the landscape of string theory, a vast space of possible physical laws. The landscape contains an estimated 10,500 different possible vacuum states, each corresponding to a different set of physical laws and constants. If eternal inflation samples all of these possibilities, then the multiverse would contain bubble universes, exploring every conceivable way that physics could operate. Our particular set of physical laws would be just one point in this vast landscape of possibilities. Most bubble universes in this landscape would be sterile, unable to support complex structures like atoms, stars, or life. The constants of physics in our universe appear to be fine-tuned for complexity. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If the strong nuclear force were slightly weaker, complex nuclei couldn't form. In the multiverse, we exist in one of the rare bubbles, where the constants allow for richness and complexity. The anthropic principle provides a framework for understanding this apparent fine-tuning. Rather than requiring that our universe be specially designed for life, the multiverse perspective suggests that conscious observers can only exist in bubble universes where the physical laws permit complexity. We observe fine-tuned constants not because the universe was designed for us, but because we can only exist in universes capable of supporting observers. The boundaries between bubble universes create regions where different physical laws meet and interact. These boundaries might produce observable signatures, patterns in the cosmic microwave background created when our bubble collided with neighboring bubbles during the early universe. Several research groups have searched for such collision signatures, though no definitive detections have been confirmed. The collisions between bubble universes would be among the most energetic events possible, releasing vast amounts of energy as different vacuum states interact. These cosmic catastrophes might completely alter the physical laws within affected regions, creating zones where hybrid physics operates according to principles from multiple bubble universes. The temporal aspects of the multiverse are equally mind-bending. Because inflation can end at different times in different regions, bubble universes have different ages relative to the inflating background. Some bubbles might be much older than ours, having nucleated and evolved for trillions of years before our universe began. Others might be much younger, just beginning their cosmic evolution as our universe enters its twilight phases. The causal structure of the multiverse prevents communication between different bubbles under normal circumstances. Each bubble universe is causally isolated from the others, evolving according to its own physical laws, without influence from neighboring cosmos. However, quantum mechanical effects might permit subtle correlations between bubble universes, creating mysterious connections across the multiverse. Recent theoretical work has explored whether advanced civilizations might be able to engineer bubble universe collisions, or even create new bubble universes. If the physics permits such cosmic engineering, then sufficiently advanced beings might be able to transcend the boundaries of their home universe and explore other bubbles in the multiverse. The observational consequences of living in a multiverse remain hotly debated among cosmologists. While we cannot directly observe other bubble universes, their existence might leave indirect signatures in our observable universe. The statistical properties of our physical constants, the patterns in cosmic structure formation, and the ultimate fate of our universe might all carry information about our multiverse context. As you contemplate the possibility that our entire observable universe is just one bubble in an infinite cosmic foam, consider that consciousness itself might be the multiverse's way of exploring its own vast landscape of possibilities. Through beings like us, the multiverse becomes aware of itself, understanding its own infinite creativity through countless perspectives scattered across countless bubble universes. The edge of our universe becomes not a boundary but a membrane, a surface separating our cosmic bubble from the vast ocean of other realities, each exploring different answers to the question of what it means to exist. What if the edge of the universe is like the edge of Earth's surface, a boundary that doesn't exist because space curves back on itself? This possibility, suggested by Einstein's general relativity, presents us with a cosmos that is finite in volume, yet has no edge, no boundary, no place where space comes to an end. Imagine living on the surface of a sphere, like a two-dimensional being confined to Earth's surface. You could travel in any direction for as long as you wanted, yet you would never reach an edge or boundary. Eventually, you would return to your starting point, having circumnavigated the globe. The surface is finite in area, but boundaryless. Every point looks like every other point, with no special locations that could be called edges. Einstein's equations allow for similar three-dimensional geometries where space curves back on itself. In a closed universe with positive curvature, space behaves like the three-dimensional analog of a sphere's surface. You could travel in any direction through space, and if you journeyed long enough, you would eventually return to your starting point from the opposite direction. The mathematics describing closed universes are beautifully elegant. Just as the two-dimensional surface of a sphere can be described by the equation x squared plus y squared plus z squared equals r squared, a closed three-dimensional universe can be described by analogous equations in four-dimensional space. The universe would have a finite volume, proportional to r cubed, but every point within it would be equivalent to every other point. In such a universe, the question, what lies beyond the edge, becomes meaningless, like asking what lies north of the North Pole. There is no edge to lie beyond because space curves smoothly back on itself. The universe would be complete and self-contained, with no external space required to contain it. This possibility was seriously considered in the early decades of the 20th century, when Einstein's cosmological equations were first being explored. Alexander Friedmann found solutions describing expanding universes with positive curvature that would grow to a maximum size and then contract back toward a big crunch. Einstein himself initially favored a static closed universe, adding his famous cosmological constant to prevent gravitational collapse. The observational evidence for or against a closed universe comes primarily from precise measurements of the cosmic microwave background. The geometry of space determines how acoustic waves propagated through the early universe, creating characteristic patterns in the temperature fluctuations we observe today. These patterns serve as a cosmic ruler, allowing astronomers to measure the overall curvature of space. Current measurements from the Planck satellite suggest that the universe is remarkably close to geometrically flat, with any curvature so small that it cannot be distinguished from zero within observational uncertainty. However, the measurements are not perfectly precise, leaving open the possibility that the universe has a very slight positive curvature that makes it closed but enormous. A closed universe would need to be vastly larger than our observable universe for the curvature to be so slight that we cannot detect it. The radius of curvature would have to be at least hundreds of times larger than our observable horizon. In such a universe, the observable universe would be like a small patch on Earth's surface, so small that the surface appears flat despite the planet's overall spherical geometry. The topology of a closed universe raises fascinating questions about cosmic structure and evolution. If space curves back on itself, then the large-scale structure of the universe, the cosmic web of galaxy filaments and voids, might show characteristic patterns related to the universe's overall geometry. Galaxies and galaxy clusters might be arranged in ways that reflect the closed topology of space. One of the most intriguing possibilities in a closed universe is the potential for cosmic repetition through space rather than time. If you could see far enough in a closed universe, you might observe the same cosmic structures appearing multiple times in different directions. The cosmic microwave background might show subtle correlations between opposite directions in the sky, created by the universe's finite size and closed topology. The evolution of a closed universe depends critically on the amount of matter and dark energy it contains. If matter dominates over dark energy, the universe will eventually stop expanding and begin contracting, leading to a big crunch where all matter and energy collapse back into a singularity. If dark energy dominates, even a closed universe can expand forever, though its geometry remains curved. Recent observations of dark energy's effects on cosmic expansion suggest that our universe will expand forever, even if it is geometrically closed. The accelerating expansion driven by dark energy overcomes gravitational attraction, preventing the collapse that would otherwise occur in a matter-dominated closed universe. This creates the paradox of a finite universe that expands eternally. The quantum mechanical implications of a closed universe are profound. In a finite universe with a finite number of quantum states, the recurrence theorem suggests that any particular quantum configuration will eventually repeat itself. This could lead to cosmic cycles, where the same patterns of matter and energy recur over enormous timescales, creating a universe that is eternally recurring rather than truly eternal. The philosophical implications of living in a closed universe are deeply moving. Rather than existing in one small corner of infinite space, conscious beings would inhabit a complete, self-contained cosmos. Every point in space would be equally significant, and the universe would form a unified whole rather than an endless expanse. The search for cosmic topology continues through increasingly sophisticated analyses of cosmic structure and the cosmic microwave background. Scientists look for patterns that would reveal whether space wraps around itself on large scales, creating characteristic signatures that would distinguish a closed universe from infinite flat space. As you contemplate the possibility of living in a curved universe that closes back on itself, consider that such a cosmos would be like a cosmic mandala, a complete, self-contained pattern where every part relates to every other part. In such a universe, the edge becomes not a boundary but a connection, linking every point in space to every other point through the gentle curvature of cosmic geometry. The question of what lies beyond the edge dissolves into the recognition that in a closed universe, everything lies within, and the within encompasses everything that can possibly exist. What if the edge of the universe is not a cosmic boundary but a computational one, the limit of processing power in a vast simulation that contains everything we know as reality? This startling possibility, seriously considered by philosophers and physicists, suggests that our entire cosmos might be a digital construction running on some unimaginably powerful computer system. The simulation hypothesis gained prominence through the work of philosopher Nick Bostrom in the early 2000s, but its implications for cosmic boundaries are profound and unsettling. If our universe is indeed a simulation, then its edge would be determined not by physical laws, but by computational resources, memory, processing power, and the algorithms that govern how simulated reality behaves. In a simulated universe, the apparent vastness of space might be an illusion created by clever programming. Just as video games can create the impression of vast worlds that are actually composed of relatively small amounts of data, a cosmic simulation might use computational tricks to create the appearance of billions of galaxies, while actually processing only a tiny fraction of that data at any given time. The concept of level of detail scaling, common in computer graphics, could explain how a simulated universe manages computational resources. Distant galaxies might be rendered as simple statistical patterns rather than detailed structures, with full complexity generated only when conscious observers direct their attention towards specific regions. This would create a universe that appears infinite and detailed from within, but requires only finite computational resources to maintain. The edge of a simulated universe might manifest as subtle glitches or artifacts that reveal the underlying computational nature of reality. These could take many forms: pixelation at the smallest scales of space and time, quantization of physical properties that should be continuous, or strange correlations between distant events that suggest common computational origins. Some theorists have speculated that the discrete nature of quantum mechanics itself might be evidence of digital simulation. The quantum nature of matter and energy, with its discrete energy levels and probabilistic behavior, resembles the way digital computers process information. The uncertainty principle might reflect computational approximations rather than fundamental physical properties. The apparent fine-tuning of physical constants in our universe could be explained by simulation parameters chosen by the programmers to create interesting and complex behavior. Rather than requiring anthropic explanations or multiverse theories, the values of fundamental constants might simply be the result of deliberate choices made by beings running the simulation to study complex systems and emergent phenomena. The computational requirements for simulating a universe would be staggering by current technological standards, but they might not be prohibitive for sufficiently advanced civilizations. If Moore's law continues for even a few more centuries, the computational power available to future civilizations could exceed current capabilities by factors of trillions or more. The boundaries of a simulated universe might be designed to be undetectable from within the simulation. The programmers could implement boundary conditions that prevent simulated beings from reaching the edges of the computational domain. Space could be programmed to expand faster than any simulated object can travel, creating the illusion of an infinite universe while maintaining finite computational requirements. Alternatively, the simulation might use periodic boundary conditions, like those common in scientific simulations. In such a universe, traveling far enough in any direction would eventually bring you back to your starting point, but the wrapping might be so subtle and occur at such vast scales that it would be undetectable to inhabitants. The resolution limits of a simulated universe would create natural boundaries to observation and measurement. Just as digital images have pixel limits, beyond which no additional detail exists, a simulated cosmos might have fundamental resolution limits that prevent observers from probing beyond certain scales of space, time, or energy. These limits might manifest as the Planck scale in our universe. The processing of time in a simulated universe raises fascinating questions about the nature of temporal boundaries. The simulation might process time in discrete steps, creating a granular flow of moments rather than smooth temporal continuity. The rate of this processing might vary depending on computational load, creating subtle variations in the flow of time that would be undetectable to simulated observers. Memory limitations in the simulation could create boundaries to the persistence of information. Events that occurred very long ago or very far away might be deleted from the simulation's memory banks to conserve computational resources. This could explain why the universe appears to have a finite age and why information from beyond certain cosmic horizons is unavailable. The question of consciousness in a simulated universe is particularly perplexing. If consciousness can emerge from sufficiently complex information processing, then simulated beings might be genuinely conscious rather than mere philosophical zombies. This raises ethical questions about the responsibilities of beings running cosmic simulations and the reality of suffering and joy within simulated worlds. The hierarchy of simulation raises the possibility of nested realities. If advanced civilizations create simulated universes, and those simulated universes eventually develop their own advanced civilizations that create their own simulations, the result could be a vast hierarchy of nested realities. Statistical arguments suggest that most conscious beings would exist in simulations rather than base reality. Detection of simulation boundaries might be possible through careful observation of apparent violations of expected physical behavior. Slight correlations between distant quantum events, unusual patterns in cosmic structure, or subtle glitches in the behavior of fundamental particles might reveal the computational substrate underlying apparent reality. The ultimate boundary of a simulated universe would be the physical computer system running the simulation. This raises profound questions about the nature of the reality containing the computer. Is that reality itself simulated? How many levels of simulation might exist before reaching base reality? These questions push the boundary concept to its ultimate limits. As you contemplate the possibility that your entire experience of existence might be patterns of information processed in a vast computer, consider that the meaningfulness of experience might not depend on its substrate. If consciousness and meaning can emerge from information processing, then simulated beings might be as real and significant as beings in base reality. The edge of a simulated universe becomes not a physical boundary, but an information boundary, the limit where data ends and the void of unprocessed possibility begins, maintained by the computational resources of beings whose nature and motivations remain utterly mysterious to the conscious patterns living within their digital cosmos. At the smallest conceivable scales of space and time, the smooth fabric of space-time that we experience gives way to something far stranger, a seething quantum foam, where the very concepts of distance, duration, and boundary lose their familiar meanings. This is the Planck realm, where quantum mechanics and gravity merge into a maelstrom of uncertainty that might represent the ultimate edge of physical reality itself. The Planck scale, defined by fundamental constants of nature, marks the boundary where our current physics breaks down completely. At distances smaller than the Planck length, roughly 10, -35 meters, and timescales shorter than the Planck time, about 10, -43 seconds, quantum fluctuations in the gravitational field become so violent that space and time themselves become uncertain quantities rather than fixed background stages. At these scales, the notion of a smooth, continuous space-time becomes meaningless. The energy density of quantum fluctuations becomes so enormous that it curves space-time into a bubbling foam of microscopic black holes and wormholes that appear and disappear faster than any measurement could detect them. The geometry of space at the Planck scale resembles a cosmic ocean during a storm, with waves and turbulence operating at every possible frequency. This quantum foam suggests that space itself might be granular rather than continuous, composed of discrete units of volume that cannot be subdivided further. Just as matter is made of atoms and energy comes in quantum packets, space might be made of fundamental spatial units with dimensions on the order of the Planck length. Below this scale, the concept of smaller might simply have no meaning. The implications for cosmic boundaries are profound. If space is fundamentally granular, then the edge of the universe might not be a smooth surface, but a pixelated boundary where space literally comes to an end at the resolution limit of space-time itself. Beyond this boundary, there would be no space to contain anything, not emptiness, but the complete absence of the spatial concepts that allow for containment. Loop quantum gravity, one of the leading approaches to quantum gravity, describes space-time as a network of discrete geometric relationships rather than a smooth continuum. In this picture, space is woven from quantum threads that form a fabric with finite resolution. The universe would be like a vast three-dimensional tapestry, with quantum foam representing the finest scale at which the weaving operates. String theory suggests an alternative picture where the fundamental components of reality are not particles, but vibrating strings or higher dimensional membranes. In this framework, the apparent smoothness of space-time emerges from the averaged behavior of countless quantum strings vibrating in higher dimensional space. The Planck scale represents the resolution limit where individual string effects become apparent. The extra dimensions predicted by string theory might provide space for the universe to extend beyond our three-dimensional experience. The boundary of our observable three-dimensional space might be permeable to influences from these higher dimensions, creating subtle effects that we interpret as dark matter, dark energy, or other mysterious phenomena. Emergent space-time theories propose that space and time are not fundamental features of reality, but emerge from more basic information processing relationships. In these approaches, the Planck scale might represent the transition between emergent space-time and the underlying computational substrate that creates the illusion of spatial and temporal continuity. The holographic principle suggests that all the information in any volume of space can be encoded on its boundary surface. At the Planck scale, this principle might reach its ultimate expression, with each Planck-sized region of space containing exactly one bit of information. The boundary of the universe would then be an information surface containing the complete description of everything within it. Causal sets theory proposes that space-time is fundamentally composed of discrete events, connected by causal relationships, rather than continuous geometric structure. In this picture, the boundary of the universe would be the set of events that have no causal successors, the final moments in the causal evolution of cosmic structure. The uncertainty principle creates fundamental limits to how precisely the boundary of space can be defined. Any attempt to measure the exact location of a cosmic boundary would require enormous energies that would themselves create new spatial structures, making the boundary indefinite. The edge of the universe becomes subject to quantum uncertainty in the same way that particle positions and momenta are uncertain. Quantum tunneling effects at the Planck scale might allow space itself to tunnel beyond its apparent boundaries, creating new regions of space-time spontaneously. This could make any cosmic boundary fundamentally unstable, with new space continuously bubbling into existence at the quantum level through processes that violate classical causality. The measurement problem in quantum mechanics becomes especially acute when applied to cosmic boundaries. Who or what constitutes the observer that collapses the quantum state of the universe's edge? Without conscious observers to define classical boundaries, the edge of the universe might exist in a quantum superposition of all possible boundary conditions simultaneously. Virtual particles, which pop into existence and annihilate throughout quantum space, become especially important near boundaries, where energy conservation can be temporarily violated. Near the edge of the universe, virtual particle creation might be enhanced, potentially creating observable effects that could reveal the presence of nearby cosmic boundaries. The vacuum state of quantum field theory is not empty space, but a seething ocean of quantum fluctuations. Near cosmic boundaries, these fluctuations might be modified by boundary conditions, creating observable signatures in the cosmic microwave background or other high-precision measurements. Quantum entanglement between regions inside and outside cosmic boundaries could create non-local correlations that transcend spatial separation. Information about what lies beyond the edge might be encoded in the quantum correlations of particles within our observable universe, though extracting this information might be practically impossible. As you contemplate these quantum effects operating at the foundation of spacetime itself, realize that the boundary between existence and non-existence might be far more subtle and dynamic than our classical intuitions suggest. At the deepest level, the edge of the universe might not be a place or a surface, but a quantum process, a continuous dance of creation and annihilation that defines the boundary between being and possibility through the fundamental uncertainty that characterizes all quantum phenomena. The quantum foam suggests that the ultimate edge of reality is not a wall but a transition, a place where the classical concepts of space, time, and boundary dissolve into the pure potentiality from which all structure emerges. Imagine embarking on the ultimate journey, a voyage to the edge of the universe itself. What would such a journey entail? And what would you discover when you arrived at the cosmic frontier? The physics of such an expedition reveals fundamental truths about the nature of space, time, and the limitations imposed by the structure of reality itself. The first challenge you would face is the simple fact that the edge of the observable universe is constantly receding. As you travel toward any distant galaxy, cosmic expansion carries it away from you at a rate that increases with distance. For the most distant observable galaxies, this recession velocity exceeds the speed of light, meaning that no matter how fast you travel, you can never actually reach them. Even if you could travel at the speed of light, the cosmic speed limit imposed by special relativity, you would find yourself in a cosmic version of Zeno's paradox. The edge of the observable universe would retreat before you at exactly the same rate you approach it. Light from regions beyond your starting point would continue to reach you, expanding your observable universe as you travel, but the ultimate edge would remain forever beyond your reach. The expansion of space itself creates this fundamental barrier. Unlike motion through space, which is limited by the speed of light, the expansion of space has no such restriction. Space can expand at any rate, carrying matter and energy along with it. This means that sufficiently distant regions are being carried away from us faster than any signal or traveler could ever reach them. The mathematics of cosmic expansion reveal that there exists an event horizon in cosmology, a boundary that separates regions we can theoretically reach from regions that remain forever beyond our causal influence. In an accelerating universe driven by dark energy, this event horizon is currently located at about 16 billion light-years from Earth, well within our observable universe but forever unreachable by any physical journey. Consider attempting to travel to a galaxy currently 20 billion light-years away. Even if you could travel at 99.9% the speed of light, cosmic expansion would carry that galaxy further away during your journey. By the time you covered the initial 20 billion light-year distance, the galaxy would be perhaps 30 billion light-years away. You would be engaged in an eternal chase across an expanding cosmic landscape. The relativistic effects of high-speed travel would add strange dimensions to your cosmic journey. As your velocity approached the speed of light, time dilation would cause time to pass more slowly for you relative to the rest of the universe. From your perspective, the journey might take only decades or centuries, but billions of years would pass in the external universe during your voyage. This time dilation means that even if you could somehow reach the edge of the currently observable universe, you would arrive to find a cosmos radically transformed by eons of evolution. Stars would have been born, lived their entire lives, and died. Galaxies would have merged and evolved. The cosmic microwave background would have cooled to undetectable temperatures. You would arrive at the edge of a universe that no longer resembled the one you left behind. The energy requirements for interstellar travel, let alone cosmic edge travel, are staggering. Accelerating even a small spacecraft to relativistic velocities requires energies comparable to the entire current energy production of human civilization. Reaching the cosmic edge would require energy resources that dwarf anything available to planetary civilizations. Generation ships, spacecraft designed to carry entire populations across cosmic distances over thousands or millions of years, represent one approach to extreme cosmic travel. But even generation ships would face the impossibility of reaching the cosmic edge due to expansion effects. The journey would become an eternal voyage through an ever-expanding cosmic ocean. The psychological challenges of cosmic edge travel would be unprecedented. Travelers would face the ultimate form of cosmic loneliness, journeying away from everything familiar toward a destination that recedes faster than they can approach it. The knowledge that return would be impossible, that home would be unreachable across the expanded space, would create profound existential challenges. Communication with home would become increasingly difficult and eventually impossible. Radio signals would become redshifted by cosmic expansion, losing energy and shifting to lower frequencies during their journey across expanding space. Eventually, the expansion would stretch the wavelengths beyond any conceivable detection threshold. The cosmic expansion also means that the traveler's view of the universe would continuously change during their journey. Galaxies behind them would appear increasingly redshifted and dimmed by expansion effects. Eventually, the cosmic microwave background itself would be redshifted beyond detection, leaving the travelers in a cosmos that appears increasingly empty and dark. Advanced propulsion technologies, matter-antimatter drives, fusion ramjets, or even more exotic possibilities like manipulating space-time itself might extend the reach of cosmic travelers. But even the most advanced conceivable technologies cannot overcome the fundamental limitation imposed by cosmic expansion and the finite speed of light. The ultimate irony of traveling to the cosmic edge is that the journey would create its own form of cosmic loneliness. The faster and farther you travel, the more you would be isolated from the cosmic community of galaxies and civilizations. You would become a lonely island of consciousness, racing through an expanding void toward a destination that retreats before you. Quantum mechanical effects might provide alternative approaches to reaching cosmic boundaries. Quantum tunneling, wormhole creation, or manipulation of the quantum structure of space-time itself might theoretically allow instantaneous travel across cosmic distances. However, such technologies remain purely speculative and might be prohibited by fundamental physical principles. As you contemplate the impossibility of physically reaching the cosmic edge, consider that the journey itself might be more meaningful than the destination. The attempt to reach the ultimate frontier would be an expression of consciousness, pushing against its own limitations, exploring the boundaries not just of space, but of possibility itself. The cosmic edge remains forever beyond physical reach, but it calls to consciousness as the ultimate frontier, not a place to visit, but a concept that challenges us to understand our place in an expanding universe, where the very meaning of distance and boundary is transformed by the dynamic nature of space-time itself. Imagine for a moment that you could somehow position yourself at the very edge of the observable universe, 46.5 billion light-years from Earth. Looking back toward home across the vast expanse of cosmic history, what would such an impossible observer see? The view from this ultimate vantage point would reveal the universe in ways that challenge every assumption about perspective, causality, and and the nature of observation itself. From this cosmic edge, Earth and our entire local region of space would appear as they existed billions of years ago. The light reaching an edge observer from our solar system would show Earth during its earliest epochs, perhaps even before life began. Our sun would appear much younger, our galaxy would have a different structure, and the entire local cosmos would be caught in an ancient moment of cosmic time. The observer at the edge would witness the universe in reverse temporal order from our perspective. While we look outward and see increasingly ancient cosmic epochs, the edge observer looking toward us would see a time-reversed cosmic movie. Galaxies would appear to be growing younger, stars would be assembling rather than dying, and the overall evolution of cosmic structure would seem to run backward. This temporal reversal creates paradoxes that reveal the profound relativity of cosmic observation. There is no absolute now that extends across cosmic distances. Simultaneity is relative to the observer's position and motion. What we consider the current state of the universe exists only from our local perspective. An observer at the cosmic edge would have an equally valid but completely different perspective on cosmic time. The cosmic microwave background would present a particularly interesting puzzle for an edge observer. From their vantage point, this radiation would not appear as a uniform background, but as a directional signal coming from the region containing Earth and our local cosmic neighborhood. They would see the universe's earliest light not as surrounding them uniformly, but as emanating from one particular direction in space. The edge observer would exist in a region of space that appears nearly empty, from our perspective beyond the reach of our most powerful telescopes, at the very limit of our observational horizon. But from their local perspective, they would be surrounded by galaxies and cosmic structure, just as rich and complex as what we observe around Earth. Their local universe would appear normal and hospitable. The gravitational effects experienced by an edge observer would be fascinating to consider. They would exist in a region where the large-scale gravitational influence of our local supercluster would be minimal, but they would be subject to the gravitational effects of their own local cosmic environment. The cosmic web of dark matter would extend through their region, just as it does through ours. Communication between Earth and an edge observer would be fundamentally impossible due to cosmic expansion. Any signal sent from Earth toward the edge would be stretched and redshifted by the expansion of space during its journey. By the time such a signal could theoretically reach the edge, it would be redshifted beyond any conceivable detection threshold. The edge observer would face the ultimate form of cosmic loneliness. Not only would they be isolated from Earth by distance and time, but the accelerating expansion of the universe would ensure that their cosmic isolation increases with every passing moment. Galaxies near them would be carried away by expansion, just as galaxies near us are being carried beyond our future event horizon. The view of cosmic structure from the edge would reveal patterns invisible from our Earth-bound perspective. The edge observer might see large-scale correlations in galaxy distributions that span our entire observable universe, patterns that we cannot detect because we exist within them rather than viewing them from outside. Dark matter and dark energy would affect the edge observer just as they affect us, but their local manifestations might be different. The dark matter halos surrounding galaxies in their region might have different properties due to the different cosmic environment and evolutionary history. Dark energy's effects on local cosmic expansion would be the same, but the cosmic context would be completely different. The edge observer would confront the same cosmic mysteries that puzzle us: the nature of dark matter and dark energy, the origin of cosmic structure, the ultimate fate of the universe. But their perspective might provide insights unavailable to Earth-bound observers. They might see aspects of cosmic evolution that are hidden from our perspective within the cosmic web. Time dilation effects would create additional complications for edge observations. Due to the different gravitational environment and cosmic expansion history at the edge, time might flow at a slightly different rate compared to Earth. This would create subtle but measurable differences in how cosmic evolution appears from the two vantage points. The quantum mechanical implications of edge observation are particularly intriguing. Quantum entanglement between particles at Earth and particles at the cosmic edge would create non-local correlations spanning the entire observable universe. The measurement of quantum states at the edge might instantaneously affect quantum states near Earth, creating a form of cosmic-scale quantum mechanics. The edge observer would face fundamental questions about the nature of their own existence. How did matter and energy reach such an extreme cosmic location? What processes led to the formation of galaxies and potentially life at the very edge of space? Their existence would represent an extreme case of cosmic evolution operating under the most challenging conditions. The psychological experience of an edge observer would be unlike anything imaginable from our terrestrial perspective. They would know that they exist at the absolute frontier of space and time, surrounded by the ultimate cosmic wilderness. Every direction they could look would either show ancient light from the cosmic interior or extend beyond into the unknown realm beyond the edge. The edge observer would be the ultimate cosmic explorer, positioned at the boundary between the known and unknown, between existence and whatever lies beyond. Their observations would be forever limited to what lies interior to their position, with the cosmic edge always at their back, invisible and unknowable. As you imagine this impossible perspective from the cosmic edge, consider that such an observer would be conscious of the same universe we inhabit, yet their experience would be completely transformed by position and perspective. They would remind us that the universe has no center, no preferred vantage point, and that every location in the cosmos offers its own unique window into the mystery of existence. The human mind, evolved to navigate the finite landscapes of Earth, struggles with concepts of cosmic infinity and ultimate boundaries in ways that reveal profound truths about consciousness itself. When we contemplate the edge of the universe, we are not just exploring cosmology, we are probing the limits of human comprehension and confronting our deepest psychological needs for closure, meaning, and spatial orientation. Our brains evolved to understand boundaries, edges, and finite spaces. From the earliest moments of human development, we learn to navigate by recognizing boundaries between self and other, inside and outside, here and there. Our cognitive architecture is built around the assumption that everything has limits, that every space has edges, that every journey has a destination. This boundary-seeking nature of human cognition creates what psychologists call cognitive closure, our need to resolve uncertainty and ambiguity. When faced with concepts like infinite space or boundaryless geometries, our minds instinctively search for edges, walls, or limits that would make these concepts manageable. The idea of truly infinite space without boundaries triggers a form of conceptual vertigo. The terror and fascination we feel when contemplating cosmic infinity reflects what philosophers call the sublime, an aesthetic experience that overwhelms our ability to comprehend while simultaneously inspiring awe and wonder. The cosmic sublime emerges when we attempt to grasp scales so vast that they exceed our mental capacity, creating a mixture of fear and exhilaration. Children often ask, "What's beyond the edge of the universe?" because their developing minds naturally assume that everything must have boundaries. As we mature, we learn to suppress this question or accept abstract answers, but the psychological need for cosmic boundaries never fully disappears. It lurks beneath our scientific understanding, creating anxiety about ultimate questions. The human need for centers and edges manifests in how we describe the universe. We speak of Earth as our home in space, the solar system as our neighborhood, and our galaxy as our local cosmic community. These metaphors impose human-scale concepts of location and belonging onto cosmic structures that have no inherent centers or boundaries. Different cultures have developed various psychological strategies for coping with cosmic infinity. Some religious traditions create symbolic boundaries through concepts of heaven and earth, while others embrace infinity as a reflection of divine transcendence. Scientific materialism attempts to replace psychological comfort with intellectual understanding, but the emotional need for cosmic boundaries persists. The psychological impact of different cosmic scenarios varies dramatically. An infinite universe creates anxiety about meaninglessness and our cosmic insignificance. A finite but boundaryless universe challenges our basic concepts of inside and outside. A simulated universe questions the reality of our experience itself. Each possibility triggers different psychological responses. The anthropic principle, the idea that the universe must be suitable for observers because we exist to observe it, partially reflects our psychological need to feel significant and central to cosmic purpose. Rather than accepting that we might be peripheral accidents in a vast cosmos, The anthropic perspective places conscious observers at the conceptual center of cosmic explanation. Claustrophobia and agoraphobia, fears of confined and open spaces respectively, find their ultimate expression in cosmological anxiety. Some people find infinite space terrifying because it offers no boundaries or refuge, while others find closed universes claustrophobic because they impose ultimate limits on possibility. Both responses reveal how cosmic geometry affects psychological well-being. The temporal dimension of cosmic boundaries creates additional psychological challenges. The fact that cosmic edges are also temporal boundaries, places where we see the universe as it existed billions of years ago, challenges our intuitive understanding of space and time as separate concepts. This temporal displacement creates a form of cosmic jet lag that our minds struggle to process. Death anxiety, our fear of personal annihilation, becomes amplified when we consider cosmic boundaries and ultimate fates. If the universe itself has edges or endings, it suggests that even the largest scales of existence are subject to limitation and termination. This cosmic mortality creates existential anxiety that extends far beyond personal concerns. Conversely, the possibility of infinite cosmic space and time can provide psychological comfort by suggesting that existence itself might be eternal and limitless. Some people find meaning in the idea that consciousness and complexity might recur infinitely throughout infinite space, creating a form of cosmic immortality through repetition. The search for extraterrestrial intelligence partly reflects our psychological need to populate the cosmic void with companions. The apparent emptiness of space becomes less terrifying if we imagine it filled with other conscious beings facing similar questions about cosmic boundaries. SETI becomes a search for cosmic companionship as much as scientific discovery. Virtual reality and simulation technologies are beginning to provide new ways of experiencing cosmic scales psychologically. By creating immersive experiences of traveling through space or viewing cosmic structure from impossible perspectives, these technologies might help human consciousness adapt to cosmic scales that exceed our evolutionary capacity for comprehension. The mathematical nature of cosmic boundary discussions provides psychological distance from the overwhelming reality of cosmic scales. By translating infinite space into equations and cosmic geometry into mathematical relationships, we create manageable abstractions that allow intellectual engagement without emotional overwhelm. Meditation and contemplative practices often involve exercises in expanding awareness beyond normal boundaries, dissolving the sense of self into larger wholes, experiencing consciousness as unbounded. These practices might prepare human psychology for more comfortable engagement with cosmic infinity by training the mind to release its need for finite boundaries. The philosophical implications of cosmic boundaries ultimately reflect back on the nature of consciousness itself. Our ability to conceive of cosmic edges, even when they exceed our capacity for full comprehension, reveals something remarkable about the scope of human awareness. Consciousness appears to be the only phenomenon in the universe capable of contemplating the universe's own boundaries. Artistic and creative responses to cosmic infinity often succeed where purely rational approaches fail. Poetry, music, and visual art can evoke the experience of cosmic sublime without requiring complete intellectual comprehension. Art becomes a bridge between human psychology and cosmic reality. As you reflect on your own psychological responses to cosmic boundary questions, notice how these vast scales affect your sense of meaning, significance, and emotional well-being. The edge of the universe becomes a mirror, reflecting not just cosmic structure, but the nature of consciousness itself, its capacity for wonder, its need for orientation, and its remarkable ability to contemplate realities that exceed its grasp. Our psychology reveals that the search for cosmic boundaries is ultimately a search for understanding ourselves and our place in existence, a quest for meaning that transcends the physical properties of space and time. As our journey to the ultimate frontier draws to a close, we find ourselves in a remarkable position. We began tonight asking what lies beyond the edge of the universe, and we've discovered that this simple question opens into a vast landscape of possibility, mystery, and profound implications for our understanding of existence itself. The beauty of this exploration lies not in finding a single, definitive answer, for perhaps no such answer exists, but in discovering the richness and complexity hidden within the question itself. We've learned that the edge of the universe is not one boundary but many: the horizon of observation, the limit of causal influence, the boundary of physical law, the edge of computational possibility, the transition between classical and quantum reality. Each potential answer we've explored reveals different truths about the nature of existence. If infinite space extends beyond our horizon, filled with endless variations on cosmic themes, then we live in a universe of unlimited creativity, where every possibility finds expression somewhere in the vast expanse. If we inhabit one bubble in an eternal multiverse, then our reality is just one note in an infinite symphony of different physical laws and cosmic possibilities. If space curves back on itself, creating a finite but boundaryless cosmos, then we exist in a complete, self-contained universe where every point connects to every other point through the gentle curvature of space-time. If we live in a cosmic simulation, then consciousness and meaning can emerge from pure information processing, revealing the deep connections between mind and computation. If quantum foam marks the ultimate boundary, where space and time dissolve into uncertainty, then the edge of existence is not a place but a process, a continuous dance of creation and annihilation that defines the boundary between being and possibility. Each of these possibilities carries profound implications for how we understand our place in the cosmos and the nature of consciousness itself. The scientific journey we've taken tonight reveals the remarkable power of human intellect to probe questions that seem utterly beyond our scale and capacity. Through mathematics, observation, and careful reasoning, we can explore territories that no spacecraft could ever reach and contemplate realities that exist at scales trillions of times larger than our solar system. Yet our exploration has also revealed the limits of scientific knowledge and the irreducible role of mystery in our cosmic understanding. Some questions might be fundamentally unanswerable from within the system they describe. If we are part of the universe, there might be aspects of its totality that remain forever beyond our comprehension. This recognition of limits doesn't diminish the value of our exploration, it enhances it. The questions we cannot answer completely remind us that existence contains mysteries that transcend even our most sophisticated theories and observations. These mysteries preserve a sense of wonder and humility that keeps our cosmic perspective alive and dynamic. The philosophical implications of our journey extend far beyond cosmology into the deepest questions of meaning and significance. If the universe has no ultimate edge, what defines our existence? If consciousness can contemplate boundaries that exceed its comprehension, what does this reveal about the nature of awareness itself? We've discovered that the search for cosmic boundaries is simultaneously a search for the boundaries of consciousness, meaning, and significance. In asking what lies beyond the edge of the universe, we're really asking what lies beyond the edge of our understanding, our experience, our capacity for comprehension. The temporal dimension of cosmic boundaries, the fact that looking far into space means looking far into the past, reveals the deep interconnection between space and time, between cosmic structure and cosmic history. The edge of the universe is not just a spatial boundary but a temporal one, marking the limits of how far back in cosmic time we can see. This temporal aspect reminds us that we are not separate observers of cosmic evolution but participants in it. The atoms in our bodies were forged in stellar furnaces billions of years ago. The carbon that forms our cells, the oxygen in our blood, the calcium in our bones all originated in cosmic processes that span the entire history of the universe. Our consciousness represents a remarkable development in cosmic evolution, the emergence of awareness, capable of contemplating its own cosmic context. Through beings like us, the universe becomes conscious of itself, questions its own nature, and explores its own boundaries. We are not external observers of cosmic mysteries, but expressions of the universe's capacity for self-awareness. The practical implications of our cosmic boundary exploration extend to how we live our daily lives and understand our relationships with each other and the natural world. If we exist in infinite space, containing infinite variations, then every moment of consciousness, every act of love and creativity, every experience of beauty and meaning occurs infinitely many times throughout the cosmos. This repetition doesn't diminish significance, it amplifies it. The patterns of meaning that emerge from consciousness and complexity are not rare accidents but fundamental features of cosmic evolution. Love, beauty, understanding, and creativity appear to be natural expressions of how the universe organizes information into conscious experience. The environmental implications of cosmic perspective become clear when we realize that Earth represents our only known oasis of complexity and consciousness in the vast cosmic ocean. Whether the universe is infinite with endless inhabited worlds or finite with rare pockets of life, our planet remains precious beyond measure as the one place we know for certain where consciousness has emerged to contemplate cosmic boundaries. Future generations will continue this exploration with tools and perspectives we can barely imagine. Advanced telescopes might probe deeper into cosmic history. Quantum computers might simulate cosmic evolution with unprecedented accuracy. New mathematical frameworks might reveal aspects of cosmic structure that remain hidden from our current theories. Yet the fundamental questions will likely persist. Even with perfect knowledge of cosmic structure and evolution, the question of what lies beyond the ultimate boundary might remain as mysterious as ever. Some questions might be features rather than bugs in the cosmic operating system, permanent invitations to wonder rather than problems to be solved. The emotional and spiritual dimensions of cosmic boundary exploration remind us that science is not just about accumulating facts, but about expanding consciousness and deepening our sense of connection to the larger whole. The awe we feel when contemplating cosmic infinity or cosmic finitude reflects something profound about the relationship between mind and cosmos. As you return from this ultimate journey, carry with you the transformed perspective that comes from contemplating the edge of everything. Whether you're brushing your teeth tomorrow morning or walking through a forest next week, remember that you're participating in cosmic processes that extend to the very boundaries of existence itself. The edge of the universe, whatever its nature, calls to consciousness as both boundary and invitation. It marks the limit of what we can know, while simultaneously inviting us to expand the boundaries of our awareness, our compassion, and our sense of cosmic citizenship. Tonight, as you drift towards sleep and dreams, let your consciousness expand to encompass the vast mystery we've explored together. In dreams, the boundaries between self and cosmos naturally dissolve, revealing the fluid relationships between awareness and existence that operate at all scales of reality. Rest peacefully in the knowledge that you are part of something unimaginably vast and beautiful, whether that something extends infinitely beyond all boundaries or curves back on itself in finite completion. The edge of the universe becomes not a limitation but a liberation.